All right, so now I'm moving towards a description of this interface between a semiconductor electrostatic qubit and Josephson junction in tie-binding mode. So basically, what we see is that we can have a chain of two coupled quantum dots, 1 and 2, and that could be easily implemented in semiconductor electronics, as with usage of CMOS transistors. And in such case, the electron position is between nodes 1 and 2. And yeah, and then if we have we can also exploit the property of electrostatic interaction for line-to-line entanglement. And in such case, we have two electron lines, and in one case, the electron is placed between 1 and 2, and in second place, electron is placed between 1' and 2'. So then we will deal with the situation where the electron tends to be anticorrelated, when electron presence at 1 will be correlated with another electron presence at 2', and electron presence at 2 will be correlated with electron presence at 1'. So then we can have a so-called two single electron lines that can have its meaning in quantum information processing. All right, and then last time we have discussed this this issue of representation of quantum information. So basically, if we have the most minimalistic system is two-level system, and traditionally the quantum state can be encoded in such a way as given here. So this reserves for the case of this plot. And in such case, the eigen, however, what is characteristic for us is that we will express the quantum state in terms by representation in tie-binding model. So what we will have is AP1 is the energy that is associated with presence at node 1, and AP2 is energy associated with presence at node 2, and there is a Hoping constant Ts that this Hoping constant is allowing for electron to hope between point 1 and 2. So this is due to tunneling. So then we have such matrix, and of course this matrix is in case of non-dissipative system shall be Hermitian, and that's the most minimalistic representation of position-based qubit that is only reserved for possible occupants of two energy levels. So then those two energy levels are expressed by this formula 2. So basically, so you can see that in case of symmetric wells, so let's say symmetric 1 and 2, then AP1 is set to AP2 is set to AP. So what we have is that simply there is AP minus TS is its ground state, and plus TS plus AP is its excited state. So then we obviously deal with simple algebra. We come into eigenenergy base. So then it's expressed in such a way. So it's a characteristic that, especially in the case of, let's say, symmetric situation, then we have +1, -1 here. So in a sense, there's an antisymmetric wave function, you can say. And in such case, in case of excited state, symmetric. So obviously it's a linear superposition of those two objects. All right, so then there is the eigenstate that can be expressed in such a way by presence of electron on left and right quantum well. And then obviously it's traditionally there is evolution of a quantum system with time. All right, so then basically that's what can be said about the situation from one single electron qubit. There is qubit to qubit interaction. I will maybe move to this description slightly later. But in the meantime, I will describe this concept of this interface between semiconductor qubit, position-based qubit, and Josephson junction. So most minimalistic model of Josephson junction is the case of situation where we have a left and right superconductor, and clearly there is a tunneling channel in between. In this particular model, this tunneling channel is expressed in such a way that it's basically a non-superconducting state. So as we know, there is a Andrew-bound state in every Josephson junction, and this Andrew-bound state is the case of electron moving from normal state to a superconductor that is being reflected as a hole, and again, hole moving from a normal metal to superconductor is reflected as electron. So there is well, maybe I will refer to some. Yeah, so that's existence of Andrew-bound state is a kind of necessary condition for the occurrence of a Josephson effect. And then, quite obviously, we are arriving to a situation where we have simply we need to deal with description of the situation, and then the natural description comes from BCS theory. So BCS theory, Barton-Cooper-Schrieffer theory, theory of superconductivity, it formulates the superconducting state as object, as physical situation that in which two electrons are paired, so they can create a kind of quasi-boson. In such case, this will lead you to the situation where it will basically lead you to the Bogoliubov-Dijen equations, and in these equations, then you have a wave function of electron and hole, UN and VN, and basically these wave functions are interconnected by so-called superconducting order parameter. So that there is a delta X on its anti-diagonal, and there is H0 is and this H0 is Hamiltonian of free particle. So there's also assumption in those equations that there is a kind of symmetry between electrons and holes, and that at first electrons have and holes has the same effective mass, and basically hole is kind of representing anti-electron, or reversely, I mean electron is representing anti-hole. So basically this equation has a kind of structure of this equation has a structure of a kind of Dirac equation, and a kind of similarity, let's say, maybe not a structure, because Dirac equation still has a first order derivative, and H0 can be kind of Hamiltonian as present in a Schrödinger formalism. Yeah, it shall be underlined there are various variations of Bogoliubov-Dijen equations, and at this stage, we have this kind of freedom which particle we describe, and this kind of dispersion relation is hidden in this H0 Hamiltonian operator. Then obviously this superconducting symmetry is kind of present in delta X, and delta X in most simple case is S wave, which is a kind of isotropic BCS superconductor, ASPB, for example. But obviously we can move towards more exotic versions like P wave, D wave, and F wave, and so on, so on. But we don't want to do it because we're just starting. Okay, so basically the situation is that there's a equation for superconducting order parameter delta X, and so this is delta X is a kind of scalar. It's a complex value scalar, and this it's basically this imaginary part comes from presence of magnetic field that is reflected in a vector potential. So this so then there is 1/2 minus 2 f, and which is Fermi Dirac distribution function, and En is an eigenstate. So let's say most general considerations will lead us to the eigenenergy spectrum. En square set is equal to H0 square plus delta modulus square, and then we have such situation where this superconducting order parameter plays the role of mass in kind of rest mass in a kind of particle. In any case, what is essence of this effect is that this the electrons are codependent on electron dynamics, is codependent on Hall dynamics, and this dependence is by this delta X factor. It's also important to notice that this eigenenergy spectrum, and obviously if we have a like electron sitting in a kind of square, like, well, then H0 spectrum will be discrete, which will bring that this whole En spectrum will be discrete. All right, and so what is important is that, let's say, this presence of external electrostatic potential is hidden in this H0 term. So basically it's supposed to be H0 plus some potential V over X. And this external potential, well, can arise from the presence of a single electron device in some proximity to Josephson junction. So we might have the electron that is, so let's say there's superconductor, insulator, superconductor, and there's a quantum dot A and quantum dot B, and those quantum dots are semiconductor. If there's electron presence at node 1, it will affect this states of electron and hole at point 0, 1, 2, 3. All right. So basically this presence will be incorporated into H0 operator, and now we need to find the most minimalistic model that does such things. All right. So basically we'll use. So our suggestion would be, then before, just let me know, then before, then so there was a Hamilton, H0 was represented by such type of Hamiltonian, and this was for a single electron localized between two quantum dots or two or more quantum dots. So there will be the same suggestion done here. All right, so how to do it? So basically, yes, again, semiconductor part is expressed in such a way. So there's a hopping between 1 and 2 nodes for 1 and 2 for a semiconductor qubit. There are hopping terms, and there is localized energy at node 1 and at node 2. So AP1 and AP2. All right, so I will move on. So and then we need to find the most minimalistic model. Maybe I will use some extra tricks in order to describe this this situation. So I will choose the possibility. So I have 2 degrees of freedom for semiconductor qubit, 1 and 2, and then I have like 4 degrees of freedom for state of Josephson junction. So this is 0. So presence are four nodes: 0, 1, 2, 3. So obviously, always I can go into more complicated model, but I please recognize that I want to be as simple as it is possible. So I want to extract some qualitative features from this model just by the most minimalistic model, and obviously then I can go into more complicated models and so on. So basically I will make more assumptions later. So essentially so superconducting Josephson junction is nothing else as superconducting isolator superconducting, or this could be also, so this could be like a tunneling junction, or it can be a so-called weak link. In case of weak link, we can have a superconductor, let's say normal material superconductor. So we can have a superconducting material, normal metal, non-superconducting metal, again, superconducting material, or we can have strong superconductor, weak superconductor, strong superconductor. So how to incorporate all these 3 situations into simple model? Well, I will simply assume that at nodes 0 and 3, then a superconducting order parameter delta is kind of non-zero, and I will postulate that it is as small as possible at nodes 1 and 2. All right, so what we have a situation then, so choosing such most minimalistic model, we deal with quantum state. There's nothing else so we have the following possibilities. There will be 16 possibilities. So then the whole quantum state is expressed by equation 9. All right. And then there's obviously the normalization condition that leads us to such equation as given here, and then we need to inspect the matrix structure of such interacting system. So first of all, we always deal. So the question is, let's say I will come back maybe to first situation, to the situation where, let's say, Bogoliubov division equations alone. So let me first describe only the state of Josephson junction without presence of external semiconductor qubits. So I have 4 possible states for electron. So I will have the UN will have 4 will be for them vector with 4 that will be established at 4 points, and also Vn will be vector that will be established at 4 points. So basically, I will have 8. The eigenstate that has 8 elements, and naturally I will have a matrix 8 by 8 that is that will be given here. All right, so if I only limit myself to H0, so I deal with this 4 by 4 matrix. All right, so All right. So basically, yeah, and then the structure of this matrix becomes bigger if I at the same time if I have this such states as given here. So basically, for the case of a situation, then as described here, I deal with with matrix structure. So I have to account this two states for existing of that exist in a semiconductor qubit. So basically, I will express my H0 in this Josephson junction semiconductor qubit system in such a way as given here. And here there are Hoping constants. So there is TE, which is 1, 0. This is Hoping constant between 1 and 0 nodes. And then there is TI constant 2, 1, that is Hoping between nodes 2 and 1, and so on and so on. So we see the structure of this matrix. And then the energy, localized energy for presence of electron in semiconductor qubit at node 1 is AP1, and AP2 is for node 2. So basically, we deal with such situation. And the most interesting part is the presence of electrostatic Coulomb interaction. So that's a very prominent feature. Maybe I spend some time on its explanation. So there's another trick I am using in this simplistic model that is under my consideration. So basically, as you know, the superconductors are screening this presence of external magnetic field, and are also screening the electric field, especially of small value. So here we have very delicate situation. We intentionally don't introduce the electric field to the superconductor, because this electric field is breaking down the superconducting state. So basically, what we have is, we assume that superconducting order parameter is kind of non-zero at points 0 and 3. So this will also mean that this state is effectively shielded from the presence of, from seeing this electron in a semiconductor qubit. So there are only 4 channels expressing a Coulomb-Coulomb interaction, and those channels are drawn here. So basically, that's why here I don't have any Coulomb term, and then I have Q square over A. That's and then a Q square over B that corresponds to these two different distances. Obviously, the system considered here is maximum symmetric, so I can deal with kind of I can deal with the situation where I can also have some analytical solutions of specified equations. All right, so that's so again, I have such matrices H0 for electron and for a hole. So they are on this diagonal, and the only difference is the essential difference between them is that, well, there are minus signs here because hole. So 2 electrons, there's a repulsion between 2 electrons, and Coulomb repulsion, and electrostatic interaction between electron and hole. So there's minus sign here in this in these diagonal terms. At the same time, there is if you consider the spectrum of electrons and holes, they have kind of opposite eigenenergies. So especially in non-superconducting states. So basically, it's expressed by the sign of Hoping constant. So you see, this also will be incorporated later, but this Hoping constant is supposed to have opposite value. And all right, so so basically, now the question is how to express this the existence of superconducting state. And then, so we have already two block matrices on the diagonal, and then there's necessity to express the existence of superconducting order parameter. And then what happens is that we can encode the structure of superconducting order parameter in such a way that this delta 1 operator matrix and delta 2 are given as diagonal matrices. So in such a way, we can encode this presence of superconducting order parameter at all these points 0, 1, 2, 3, right? So we are doing this, and this is very kind of nice because we have the model. We have a model that can describe as both tunneling Josephson junction interacting with single electron qubit, or we can have a weak link or something in between. There's still the issue of a chemical potential. So basically, if you have one superconductor with some narrowing that is effectively weak link, what is characteristic is that you have more or less continuous chemical potential if you move from left to right side, and you can encode you can encode this chemical potential in this H0 Hamiltonian. All right. So what we do expect? We do expect that there will be some perturbation of dynamics of electron in a hole, and that Andrew bound state will be modified. Okay, so that's kind of algebraic way. So let me first inspect some of the results. So everybody can kind of simulate this this type of equation, which I just considered for coupled semiconductor qubit and Josephson junctions. Maybe a few more remarks at the same time before I move to some numerical results. So basically, you have to realize that these Hoping constants express kinetic energy of electron or hole, or also express the kinetic energy of electron or hole if you are talking about Hoping TE and TS stands for a semiconductor Hoping constant. And but these Hoping constants are kind of referring to discrete chain of quantum dots or highly confined structure. So basically, these Hoping constants will have some discrete values. That's what you need to know. So if they do have discrete values, then you have to choose them properly. So you are still describing the realistic system. All right. So okay. So basically, what are the results? So it's yes, I didn't discuss the case of two semiconductor qubits that interact in a electrostatic way, and I will describe this thing in detail in some time. In such kind of case, we have the eigenenergy in a form as specified here if we have only two semiconductor qubits. But in case of semiconductor superconducting qubit, what is very interesting feature is then we have exchange of ground states. This exchange of ground states. So basically you see this state is a ground state for certain distances between semiconductor qubit and Josephson junction qubit, and after 0.2, there's exchange of this ground states. This exchange of ground states will lead to the situation. So this is the signature of quantum phase transition. There's a signature of quantum phase transition. So in traditional Josephson junction, in such simple BCS model, you have no presence of topological phase transition, and when you place external semiconductor qubit, what happens is that there is exchange of a ground state. So you can tune this topological phase transition by controlling the presence distance between semiconductor qubit and Josephson junction. Later, I will refer to the idea of traveling qubit in semiconductor chain of quantum dots. I will show you how to do it in more kind of practical way, because here every time you need to produce new samples, right? Okay, so there's dependence of eigenenergy spectra on distance that already indicates some possible quantum phase transition in the system under discussion. All right, so next term, next thing is, then we are playing with superconducting order parameter. So we set the distance, fixed distance between a semiconductor qubit and Josephson junction, and then what we are doing is we are changing the strength of superconducting order parameter. How to translate this? So we have such situations. So there is a modulus delta. So especially so there's modulus delta, and you see that there are some ground states, states of the lowest energy, like let's say for very small superconducting order parameter. And if you increase it, the strength of superconducting order parameter, the ground states are exchanging. So this is again the signature. This is again the signature of possible quantum phase transition. So you can control quantum phase transition by distance, geometrical distance, or you can control quantum phase transition by superconducting order parameter. How to control these things by superconducting order parameter? Well, there are two ways to affect. So I have not accounted for the existence of magnetic field in the system under description, but it's still possible. So basically, what we have is that you can first suppress superconductivity in Josephson junction by using a source of external magnetic field. That's a first feature. Or you can simply change the temperature of your cryostat, and then simply this superconducting order parameter will diminish at higher temperatures. There are at least two ways, possibly more than two ways, but it's just first two ways that comes into my mind. All right. So so in general, okay. So then in general, in most minimalistic model, we have this such effective Hamiltonian as given here. And when you look on this Hamiltonian, then there's nice attempt, like more mathematical insight. There's some that you want to look for analytical solutions. So what you have is this. So this Hamiltonian, which is shown here, is basically referring to this situation where you have this superconducting order parameter it's non-zero at nodes 0 and 3, and it's 0 at nodes 1 and 2. So in such case, okay. Right, so sorry for that. Yeah. All right, so then we have it here, and there's also possibility of having this phase imprint on. So there is possibility of existence of magnetic field in that is imposing phase difference between a left and right superconductor in Josephson junction. So here we have omitted the spin degrees of freedom. Well, it is more proper to consider them. So we are dealing with matrix 16 by 16, and if we don't account the existence of spin degrees of freedom, obviously this will become bigger matrix, twice bigger. I mean, 32 by 32 if we take into account the existence of spin degrees of freedom. So just by running a kind of Mathematica in a kind of relatively clever way, with certain, well, you can get the eigenstates and eigenenergies, and it's also interesting to see that there is emergence of entanglement between Josephson junction qubit and semiconductor qubits. So this is so-called electrostatic entanglement. There was some previous study done by me and by my co-workers on the case of entanglement appearance in the system of two coupled semiconductor qubits. So basically, if I have two semiconductor qubits, there is electrostatic entanglement that is emerging. So this was work. There's some paper analytical description of two single electron lines that I will cite, that is cited at the very end of this. Yeah, so maybe this, and also there was some work of Bartłomiej Szafran from AGH, and also some work of my collaborators like Panagiotis Gounalis and Elena Blokhina on that topic. So yeah, okay, so let me move maybe to description of this entangled states. So so this state is entangled. You need to analyze it deeper. So there are some of this 16 eigenenergies or eigenstates are entangled. Yeah, so like this state is entangled, then this 3 is entangled, 4 is entangled, 5 is entangled, 6 is entangled, 7 is entangled, 8 is entangled, but the rest of them are not, simply because there is no dependence on this electrostatic Coulomb term. All right, so that's a nice feature. Okay, let me move on. So basically, then you can tune this eigenenergies of the system by external voltage. The external voltage that you are going to apply to this to Josephson junction. So you can apply voltage that is to this plate that is joining point 0, 1, 2, and 3. So you are, in a sense, you are changing its chemical potential of non-superconducting part in Josephson junction. That's your one possible tuning ability. So then you can control VT. At the same time, you can also tune the features of semiconductor qubit. Then you have 3 degrees of freedom, and then you can tune its hopping between 1 and 2. There's TS, and then you can also tune AP1 and AP2. Just to let you know, so those things you can tune electrostatically. So you can have voltage 1 and 3 voltages applied to here. At the same time, you can also use external magnetic field to induce phase difference between semiconductor 1 and superconductor 1 and superconductor 2. All right, so let me move on. So so then there was a superconducting order parameter, and this is like let you forget about just this lines, parallel lines. Then this picture basically is natural picture that is coming in tight binding mode. But there are some nice features that are present here. So again, you have this exchange of ground energies. All right, so then let me move further. So there is next stage is this there are various ways of tuning the potential energy This is AP energies, and then then you can have nice features of eigenenergy spectra. So that's how it is. And then you can also use you can also tune eigenenergy spectra in the way that you introduce as symmetric voltages in a Josephson junction. Then also you can come across nice eigenenergy spectra of a system. All right, so you can also play with Hoping constant in superconductor. So basically, what you have is that you have eigenenergy that is depending on kinetic energy in a such a way. And again here you are able to see a kind of a quantum phase transition since ground states are exchanged. That's quite interesting feature. Personally, I never managed to come across such possible model in literature. That's kind of, I believe it's my kind of only discovery. If you have some kind of counter arguments, please let me know. All right. Yeah. So then there is this algebra of operators, and maybe yeah. So what are the possible nice features of this model? So maybe first thing that I need to, one of the main things I need to underline is there is a huge ongoing attempt to integrate the semiconductor electronics and superconducting electronics since many years. And then it's impossible to connect this superconducting electronics and semiconductor electronics because you see, and the size of superconducting order parameter, there's energy gap, and there's if you apply more than 10 milli electronvolts, most superconductors are going out of its superconducting state. And so you need to play in a delicate way. So I would say in this paper, which I was just discussing, you can play with this interaction with introduction of this electric field by means of field that is generated by electrostatic qubit. So you can inject 1, 2, 3 electrons, and in such a way their presence can be seen in dynamics of Josephson junction. So this is so-called electrostatic interface, and I would say there's also possibility for having a magnetic interface. So basically, I imagine that you already have a flux transmon qubit in IBM quantum experience that stands for a quantum chip that is superconducting, and you can couple this qubit with semiconductor qubit. So and then obviously this semiconductor qubit can be interconnected to many other semiconductor qubits. So basically, we are dealing with the scheme of hybrid semiconductor superconducting quantum computer. So it has like two subsystems, and first subsystem is semiconductor qubit and semiconductor quantum computer, and second subsystem is superconducting quantum computer. You may wonder why I am dealing with at the same time with 2 quantum computers. Well, it's already known that we have like 50 qubits in Google, in IBM and Google on one chip, perhaps even 100. But there's some challenge with scaling, further scaling. So. And also, so the size of superconducting qubit is quite big. So basically, you have the smallest possible size of Josephson junction is in range of superconducting coherence length, and that is, let's say, for some materials like traditional BCS superconductors is 1,600 angstroms, which stands for 160 nanometers. That's quite a small number. That's not so small number. And then you have, at the same time, you have a very recent CMOS technology that has the channel length of 3 nanometer. So basically, you can also think that in quite near future, the CMOS quantum computer will develop further, while this superconducting quantum computer will slightly develop, but let's say its size cannot be engineered because there are some fundamental limits. And so then we will have we might have such situation where we have a high quality superconducting system that has very low number of noise and long coherence time, but is very spacey. And we have a situation where we have single CMOS quantum computer that is a kind of more noisy, but at the same time takes much less space. And then clearly you can have certain type of quantum information processing in one type of quantum computer and in another type of quantum computer, and then you need to connect them. So you connect them by this interface, this electrostatic interface. So yeah, so let's say maybe more kind of remarks. So yeah, so I will make some remarks on this SPI paper. So there's if you Google a SPI paper, SPI Pomorski, and then this is open access paper, then the first thing that is kind of possibly useful is you can see two types of interfaces in this paper, and maybe let me switch the screen to another PDF. So yeah, maybe I will slightly describe this paper. All right. Yeah, so I hope that's now fully visible. Maybe Marek, could you please confirm by chat that it's the proceedings SPI are visible? All right. So yeah, so basically what I have is yes. So yes, so far we have discussed this the concept of single electron devices in semiconductor that are representing that can represent quantum information. So there was a chain of coupled quantum dots, quantum dot A and B. There's a channel, there's a gate. So this is basically CMOS technology. Actually, there are very nice experiments in Jülich, also in US and at RIKEN with high temperature CMOS qubits. So basically what is exploited in CMOS technology is that this anti-correlation principle. So you can have a swap gate if you have electron presence here. On another line, the electrons will try to have presence in opposite configuration. You can also implement a CNOT. So this is basically this topological definition of electrostatic position-based qubit. And yeah, I already discussed this. I already discussed these things in tight binding model. Obviously, you can go into slightly better way by Schrödinger representation, by continuous representation, but then you are dealing with integral differential equations. And in the model which was described by me, there are no integral differential equations, which basically significantly simplifies those this description, and it's from a certain point of view is very insightful. Yeah, so let's say, okay, let me maybe move to, yeah, so this in figure 9 describes two types of interfaces. Electrostatic interface, that what I was describing today. And there is possibility for having flux magnetic interface. So you can have a single electron devices that you can have a closed loop of quantum dots interacting with a closed loop of where there's at least one resistance junction. So it's like flux interaction between flux superconducting qubits. So you can have this type of interface that can be developed as well, or possibly both. Right? All right. So I believe, yeah. So so this paper essentially describes. This paper describes Schrödinger approach to Schrödinger usage of Schrödinger equation for modeling of semiconductor position-based qubits. So there's a lot of work from 2004 by Fujisawa and Peta on those subjects. So the topic is not that deeply new, but there is definitely new technology that is coming right now, and this is kind of nice that. All right, so so I guess I was talking for 1 hour. Maybe I would take some suggestions or some questions. So please give me some possible some questions or some remarks. So there's obviously a lot of space for further developments in this description of such system. This is a bit fashionable topic. This is topic of hybrid quantum systems. There are tons of modifications of this Bogoliubov-Dijon equations. You can put more nodes. You can place more types of superconducting order parameter, and so that's how it is. Yeah, so I believe this topic can be greatly extended, and yeah, yeah. So if anybody of you is interested in a possible collaboration, please let me know. I simply want to, yes, I want to move on with these models. It would be nice to have. It would be nice to have this, for example, non-equilibrium physics description of such systems. It's necessary to account for existence of noise, like charge noise in semiconductor qubit. Yeah, so there's a lot of more things that can be done. Also, you can build quantum gates on this interface in a quite nice way. Yeah. So, and maybe the last comment which I will make on this, yeah, I would try to switch this camera. Unfortunately, sometimes I do have some problems, and not always things go so well as I wish it could go. Interactive. Yeah. So you can have a like chain of 10 quantum dots in a semiconductor easily, and then you can push your wave packets. Electron wave packet closer to semiconductor to Josephson junction. And so in such way, you don't need to make always the samples, new samples. It's to change this effective distance. You can simply move the wave packets. So between chain of coupled quantum dots in a semiconductor, and then this will somehow refer to the change of distance. That's what you can do. All right, so so I suggest I will continue this topic next week. Obviously the topological states of matter are kind of interesting here, and also I would say yeah, we need to describe dynamics of a quantum gates in single electron devices in semiconductor. Yeah, and also we need to prepare ourselves for more fundamental description. So perhaps this, so far I make a kind of quantization of geometrical space into discrete points. We can formulate things in a continuous way that will be more kind of interesting and more detailed. We'll give more detailed answers. So that's all right. So if there are no questions, I suggest we can meet at the same time at 5 p.m. So maybe very few remarks to you. So there's this idea, since I'm both physicist and electrical engineer, and after PhD in Josephson junction physics, I basically organized this series of lectures or seminars that's supposed to combine the current progress in quantum technologies. I was working on the semiconductor single electron devices for one year and a half, and I'm still doing my research on this topic. And also I was working with Josephson junctions. I'm rather theoretician, but I'm both kind of experimentalist as well. And basically, you're welcome with your suggestions or with your own topics. So that basically there is a new kind of channel, quantum hardware systems channel, that was created at YouTube. Please subscribe this channel. So I welcome your proposals. You can find my email in this archive, which I just presented, or just at this channel. And also, so I hope that there could be some possible kind of future collaboration value from those meetings. So I will continue this series of seminars in the way that I can promote the development of CMOS quantum computer. And so now I'm in the stage of proposing the new type of qiskit, like software for semiconductor CMOS quantum computer, and also try to think how to extend this software that is people are using. So people are using IBM quantum experience software. So there is a nice need to extend the software for. So such interfaces as described today could be well described. All right. So there are no more questions. I wish you a good weekend, and hopefully see you next week. Thank you. Hi. So you're from which place? Can I ask you? Could you describe yourself?